Okay. Hey everybody, welcome back. So this is Wednesday's lesson. We're continuing our study of quadratics. So there's a do now or warm up. This would be up on the board. And then I'd have you try to solve it. So then we would read it. It said Bobby took out the plug in his sister's kiddie pool. The amount of water, feet cubed, left in the pool can be represented by the linear function W of t equals 220 minus 50t, where t is the time in minutes since the plug was removed. The graph of the function is shown below. So that's a graph showing how the water is emptying out of the pool. Question 1 is define the two variables in this problem. So what were the two things that change in this problem? And then find W of 0 and W of 1.5 using two methods. Find it using the equation and the graph. So you can pause if you want, but I would give you time. I might have you turn and talk and share your answers. And this has been a while, so I definitely think some people might have forgot how to do this. So we'll just go to the example. Okay, so again, I would say, what are the two things that change? What are the two variables? And if you read really carefully, it kind of says it. So did anyone say what the two variables are? Well, I think time definitely is changing, right? Because it said t is time. And what else could change? Well, he's pulling the plug, so that means what's happening to the amount of water? It's going down. So on the graph and on the, I wrote it down, is that time is independent and water is dependent. Right here. Okay, next. I wanted you to try to think and write about how to find W of 0 and W of 1.5 using two methods. So let's talk about W of 0. From our study in functions, you may have forgotten, but W of 0 tells you to put 0 in as the input. So here's our function. Put 0 in for our input. Then you just do the math, do the rule. 50 times 0 is 0. W of 0 equals 220. That means at 0 minutes, there are 220 feet of water left in the pool. That makes sense because at time 0, he hasn't pulled the plug out yet. And how could you find that using the graph, right? Hopefully you had a thought. W of 0 says when the time is 0 and it's down there on the x-axis. And a lot of people have to remember to go up on the y-axis, and there you go. 220. So that's a way to use the graph and the function to get the answer. And 1.5 is very similar. You plug 1.5 into the function. Noticing on the left side it's W of 1.5. And we only do the math on this right side where the rule is, right here. 50 times 1.5 is 7.775, and then 220 minus 75 is 145. So that tells you that at 1.5 minutes there will be 145 feet cubed of water left in the pool. Now let's use the graph to find that. So we got to find W of 1.5, so that's what 1.5 minutes, so go down there. Then you go up to find the y value, and go across. Which is actually kind of tough with the graph, but you can sort of see that it's around 1.5. Great. So that's the do now. We'll keep going. Feeling yourself to pause, rewatch this part if you want, but that's how we can use two methods to find the answers to this about times 0 times 1.5. And just to throw something in there, let's go back. Can we find how long it would take for the pool to run out of water, right? And then anyone can think of that. Where does at 1 minute is it out of water? Does 2 minutes has all the water come out? At 3 minutes has the water come out? At 4 minutes has the water come out? Getting close. And hopefully some of you see that it's right here, right after, not exactly 4.5, but pretty close. And we could actually do some math to figure that out, but for today we're not going to move forward. All right, our objective is for you to be able to graph quadratic functions and identify key features of the graph. Okay, and that's our goal for this week and next week before break. We really want to decide and notice some key features of quadratic functions. Each day we're going to take a little bit, or each 2 days we're going to take a little bit and learn another key feature, an important feature of a quadratic, which makes it unique in a lot of ways, and that's why we're studying it. So, here we go. Let's explore a roller coaster at Six Flags mathematically. A roller coaster ride has similar characteristics to that of a quadratic functions graph. Okay, so you got to picture it though, right? Remember, we saw it the last 2 days, right? We saw that with the perimeter fencing. So think about, why would a roller coaster ride have some similar characteristics of a quadratic function graph? Well, I thought it would make more sense for you to watch a video. So hopefully you've clicked the video and you're watched it. If it was in class, I'd make a big deal about this video. We put our hands up. Whoa! This first part's the most important, I would tell you, because that's the part we're going to study at first. Whoa! Whoa! We were talking about, oh, who loves whoa? Whoa! 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 Tricked you. Okay, so it goes on obviously farther than that, but we're not going to watch all of it. What we're going to, though, is focus on not that whole ride you just saw. We're going to explore the lift hill and the first drop of the roller coaster at Six Flags. So that if you watch the video again, it's when he got pulled up to the top, that first drop, and then that first hill down, that first drop. So the lift hill and that first drop. The quadratic function below calculates the height of the roller coaster after x seconds, so any number of seconds, right? So here it is, f of x, or y, equals 100 times x minus 10 times x squared. So this will tell us the height of the roller coaster after any number of seconds. So 1 second, 2 seconds, 3 seconds. It will tell us how high the roller coaster is off the ground. First, though, it's important to talk about, why is this a quadratic function? Right? So if you could talk to a neighbor or talk to yourself, how do we know this is quadratic, right? Why is this a quadratic function? Well, the first 2 lessons was to help us with that, identifying why it's quadratic. So pause it, think about it. I'm going to go over it right now. Here's a little hint. Think of the form in which the quadratic functions are written in, right? Whoop, what the heck? Okay, here we're back. Okay, so it's a quadratic function because it can be written in the standard form. We talked about it yesterday. And one other thing we're talking about later, but it's the highest power is a function of 2, anyone that's read about it. So remember, quadratics can be written in the form ax squared plus bx plus c. We've seen that before in terms of factoring. And I can rewrite that equation to negative 10x squared plus 100x plus c. And remembering from the lesson before is that c can be 0, so it's just 0 in this case. Cool, so this is quadratic. So let's see how the time and the function of the roller coaster can represent a quadratic function. So here you would either use your notebook or grab that worksheet, and we would get started. So what we're going to do is graph. We're going to make a table of the different times and heights of the roller coaster, starting at time 0, and we're going to graph the data. If you don't have a graph, you can still sketch it, or you can just watch me as I do it. But just a quick reminder, and I forget if I gave you a process column, but it's always good to have a process column. So I want to show you again how to plug in your time into your process and get the height of the roller coaster. So times 0, you're going to plug it into the function where x is, boom, boom, into the rule. You're going to do your math, and you're going to get 0 following rules of operations, right? PEMDAS, though we don't call it that, we call it rules of operations. Exponents first, then multiplication, and then subtraction. So that makes sense. At times 0, it's 0 feet off the ground. Then 1 second later, let's see how far is off the ground. So again, you take the 1, you plug it in both places for x, follows orders of operations, 1 squared 1 times 10 is 10, 100 times 1 is 100, and now it's 90 feet. And you're going to do that, here's 2, put 2 in for x in both cases, 2 squared, 4 times 10, 100, 440, gosh, 2 times 100 is 200, and now we know we got that. You're going to keep going on that table. If you want to pause now, complete the rest of the table, do it in your notebook, get some practice in. Always good to practice our orders of operations. So go, and then once you're ready, go ahead and graph that data, right? And there are a bunch of questions that I would love you to answer on your own. But in case you don't want to do it on your own, I'm going to keep going. But feel free to pause, do it all, and then come back to see how you did. So here's the table of all the values if you did it correctly. There's a table of quadratic functions. And then if you graph it, minus these two little parts over here, you should get this shape for the height and time of the roller coaster. And that should look familiar, as that's the one similar one we saw Monday and Tuesday. It's got that shape. Cool. So it's quadratic. All right. Keep going. Number 2, it says, describe how the height is changing over the time interval 0 to 10. Hopefully you wrote something that you noticed from 0 to 5 seconds, it was increasing. And then from 5 to 10, it started decreasing in a similar pattern as in the way that it increased. So we again see that repeated pattern, right, that we saw yesterday. 0, 9, 90, 160, 210, 240, 250, 240, 210, 160, 90, 0. So we see that pattern again. And this is just to reiterate some of the key features. What's the height at 3 seconds and 5 seconds? You should notice that it's at 3 seconds it's 210, and at 7 seconds it's 210. What did you notice? Well, that they're the same. Why did this occur? This occurred because the pattern in the table increased and decreased in the same way. And if you just visualize a roller coaster, everybody, right? It goes, I'll try to use the mouse, hopefully you see it, right? Like if something goes up, the way gravity works, it has to pull it down. So there'll always be, a height that repeats on the other side. And are there any other times where the heights are the same? And you should see that there are plenty. 1 and 9, 2 and 8, 4 and 6, 0 and 10. And there are actually many other fractional ones. If we did 8.5 seconds, 8.6 seconds, 8.7 seconds, 8.8 seconds, 8.9 seconds, we would see it has a lot of other ones, but these are just the whole number times. But if you thought about decimals, fractions, there'd be infinite number of matching pairs. What is the maximum height for this part of the ride? Hopefully everyone sees that it is 250 feet. What time did it occur at? 5 seconds. Now, explain. People get kind of confused on that. What do I mean by explain? Well, how did you find it? It's found by finding the highest point on the graph, right? So if you went back and looked at your graph, you would see that the highest point of that roller coaster is at the top of that graph, and that happens at 5 seconds. Now here's where we get a little interesting. Do you think it's a coincidence that the maximum height is at 5 seconds? Right, and explain. So if you didn't write anything, think about it. Like, why did it happen at 5 seconds? It's just random? Most students see, no, there's a pattern in the heights in time. The maximum height is reached at the halfway point between times 0 and 10, right? Everyone sees that's the halfway point. These are the times when the height equals 0, right? When it's back on the ground. So it went up and came back down. So it makes sense that it was right in the middle, right? What time intervals is the height of the roller coaster increasing? Okay, and this is just to bring back some of our work in chapter... What chapter was that? Chapter 2, or I forget now. But we had inequalities. I think it was chapter 2. So you can say that it's from 0 to 5. Hopefully you said 0 to 5. And this is our notation to say from 0 to 5, right? 0 is less than or equal to x, which is less than 5. And then decreasing, 5 is less than x, which is less than or equal to 10. These are and statements. Smaller number here, larger number here, and we use less thans cases. So that's just to remind you. How would you describe the shape of this graph? We kind of talked about it yesterday. And are there any features you noticed? I mean, it should be all the same features we noticed from the last one. The shape of the graph is like a hill or an upside down U. The graph increases, then decreases in a similar way. Something you may not have noticed or said is that it crosses the x-axis twice, right? It touches at 0 and 10. But it only crossed the y-axis once. And then there's that idea that I wrote down before, is that the graph is symmetrical, right? That it has symmetry, right? You can split it in half, and it matches up. Okay. This was like a little bit extra usually, but it's a good thinking one. Using the function that we had, which represents the height in feet of roller coaster story, I wanted you to find f of 11, so plug 11 in for x. And then is it possible, according to the story, to have f of 11? So we put 11 in, you do some math, and you get negative 110 feet. And we always argue as a class, is that possible for a roller coaster to be negative 110 feet? Well, if so, then it would be underground, right? It's possible for 11 seconds for it to be under the ground, right? I know if some people know the Superman or Bizarro at Six Flags, that kind of goes down. If anyone's been on it, it kind of goes underground for a little bit. So it could be. It's not possible if this ride doesn't go underground. If you look at that ride, it does not go underground. So this might not be possible, right? So there's no way to put 11 seconds in to this function because you can't get negative 110 feet below ground. Find f of negative 2. Is this possible, according to the story? Yeah, you could plug in negative 2. You get negative 240 feet, but maybe you didn't need to. You know, it's not the input. X is time. Is it possible to have negative 2 seconds? No, so negative 2 doesn't work. Is it possible to have 1/2 seconds? And this is the answer that is definitely yes. So at half a second, it's up to 47.5 feet. You can't have fractional time. And our height is good, right? So of the three of them, this is the one that's probably technically 100% possible. You can have a fraction of a time and a fraction of a feet. Okay, these are the key features. Hopefully you got a chance to graph it, and you can picture that a roller coaster goes up and down, right? Now, does it exactly model what we saw in the video? Maybe not, but it kind of does, right? I mean, it sort of does, and it's just for our idea that this is a quadratic functions graph. Okay, so we'll spend more time, but this is just a summary of when I was doing it in class. And hopefully that made sense. We'll talk more about quadratics, but you're getting a sense of what it looks like, some of the repeating patterns in the table. And we'll explore some of the other key features in a little more detail as we move through next week. So have a nice long weekend. There's no work on Friday, no quizzes. We might have a quiz next week, next Friday, right before April break. And I do know that I need to, well, I'll put it in the Google Classroom. Okay, have a great day, everybody.